In this lecture, we will understand the concept of borrow, borrower, and the referent. In Rust, you often come across the term borrowing, and we will explore what exactly is that. So, very important concept, and we will understand this with step-by-step example. Now, let's say I have a variable. Let me call it as num1, and let me initialize this to 50. And after that, let me create another variable which is a reference to num1. I'll call this as ref of num1, and I have to take ampersand here, ampersand num1. So this is called as a ref of num1. So this operation is called as a borrow operation. Here this variable borrows num1 to read its data. It cannot modify its data. This operation is called as a borrow operation, or to be precisely, it is called as immutable borrow. Why it is immutable borrow? That's because this cannot modify the content of the referent using the reference. It can only read it. That's why it is called as immutable borrow. And let's say I make this as mute. Now it's a mutable referent. So even though it is a mutable referent, this is a immutable borrow. Here this reference can only read the referent. So even though it is a mutable referent, this is mutable referent. So now let's say I try to change the content of this referent using this reference. Let's say I want to store 100 in it. So I want to modify this value. This will not work because since it's an immutable borrow, so this is also called as immutable reference in this case, and you cannot dereference the immutable reference to change the value of the referent. Hence, you will get an error here, as you can see. Cannot assign to this one which is behind immutable reference. So now how do we convert this into a mutable borrow? So if you want to convert this into a mutable borrow, then you have to mention the mute keyword after this ampersand sign. Now it becomes a mutable borrow. This is a mutable borrow, and this reference is called as mutable reference. So mutable reference means by using that reference, you can modify the value to which it refers to. That means the referent can be modified by using the reference. This is a legal code. Now you can change the value of the referent. So if you print the value of the referent, it would print 100. As you can see, it prints 100. Very simple concepts. Two concepts here. One is mutable borrow concept and another one is immutable borrow concept. So you have to use a mute keyword after this ampersand sign in order to create a mutable borrow. Then only you can use that reference to change the referent or to modify the referent. So now what if this referent is not mutable? Let's consider this condition. So here it is immutable referent. Immutable referent. Now I'm trying to do a mutable borrow out of it. So now is this code allowed? Can you identify the illegal code statement here? So the illegal code statement here is at this position. First of all, the referent is not mutable here. It is immutable. And we are trying to create a mutable borrow to it. That is not allowed because the referent is immutable. Hence, you will see an error here. As you can see, cannot borrow num1 as mutable, as it is not declared as mutable. Hence, for this condition, you cannot create a mutable borrow of the referent num1. Hence, this is not possible. You can only create immutable borrow. When you make this as immutable borrow, of course, you cannot do this. So this will trigger error. I hope you got those points. And now let's see, can we create multiple immutable borrows? Let's say this is an immutable referent and this is immutable borrow. So when it's immutable borrow, I can create any number of immutable borrow. It's like any number of readers. These are all readers. So they are only interested in reading the value of num1. They cannot modify the value of num1. So when that is the thing, you can create n number of readers or n number of immutable borrows. There is no problem in it. It won't introduce data race conditions or any undefined behavior when there are only readers. So the data races and other undefined behavior will come into play when there are multiple readers and writers. That's why the Rust borrow checker allows you to create n number of immutable borrows. No problem. All these codes are legal actually. I can make this as 2, 3, 4. There are 4 immutable borrows. So all these are legal code, and if you want to read the referent, you can just dereference that like this, and you can read the value of the num1. So n number of immutable borrows are possible. Even you can create a function. Let's say I create a function, so print value, something like that. Functions we'll cover later, don't worry about these syntaxes. So let's say I'll take an argument of type $i32 here, and I can again print it like this. Here the function borrows the num1 as read only. This is also called as borrow, another kind of borrow. Here this is just arg or asterisk you can mention. Here also you can pass the address of num1. This is also an immutable borrow. And so I have to print value like that. There seems to be some problem. I'm sorry, basically it is not returning anything, so I just have to call that. Fine. I hope you get the concept of immutable borrow. Now let me also mention about the type of these borrows. Let's say you have a mutable referent, and when I create a reference, let me call it as R1 as ampersand num1. What is the type of R1 here? Type of R1 is ampersand I32, remember that. And when I create let R2 is equal to ampersand mute num1, what's the type of R2 here? Type of R2 is ampersand mute I32. Remember that. Now we understood that we can have n number of immutable borrows to any referent, whether it is mutable referent or non-mutable referent. So when we have n number of immutable borrows, so we don't usually see any kind of data race conditions or undefined behavior. But the problem arises when we try to create multiple mutable borrows. So the borrow checker feature of the Rust compiler, it doesn't allow us to create a multiple mutable borrows, because when there are multiple mutable borrows, then there could be a chance of data race conditions and it could cause undefined behavior. There is a huge chance of introducing a lot of bugs in the code, etc. That's why I cannot do this. Let's try to create multiple mutable borrows. So let me, for a time being, let's remove that. I will create a mutable borrow. How do I do that? I'll just mention the mute keyword here. One mutable borrow is created. That means one mutable reference is created. Now let's compile this code. As you can see, it compiles, no problem. Now let's try to create another mutable borrow. So let me just copy paste this code and I'll make this as ref2. This is the first mutable borrow and this is the second mutable borrow. After that, we will try to, let's say, modify ref1. I make this as plus is equal to 1, let's say, and ref2 is equal to, let's say, 200. Then we will try to print the value of num1. So now what do you think? Will this code compile? First of all, what you need to observe here is there are two references which are holding both read and write access to the referent num1. When there are multiple writers, there is a possibility of data race condition. When there are multiple readers, then no problem. So multiple immutable borrows, no problem. But the borrow checker of Rust doesn't allow you to hold two multiple mutable borrows to the same referent. So you will see an error here if you try to compile this code. As you can see, it says cannot borrow num1 as mutable more than once at a time. Rust enforces single write or multiple read policy. Our code actually violates that rule. So we are trying to have multiple writers are there. Hence, it violates that rule. So the rule is single write or multiple read to the referent. So we learned that there could be multiple immutable borrows, but there cannot be multiple mutable borrows to the same referent. Now, what if we mix mutable and immutable borrows? So let's say in this code, I'll make this as mutable, but I'll make this as immutable. This is the first mutable borrow and this is the first immutable borrow. Now still it violates that rule. What the rule says? Single write or multiple read. So here there is a single write and there is also a single read. Hence this would violate that rule. That's why when I try to compile this, I will see the error. The error is at this location. What it says is cannot borrow num1 as immutable because it is also borrowed as mutable. So it is already borrowed as mutable here. When it is already borrowed as mutable, you cannot again borrow it as immutable. Hence, the error is at this position. What if I first borrow it as immutable and then I'll again try to take the mutable reference like this? I'll just remove this. It will cause confusion. And here I cannot do this, so I'll just comment that out. And ref2 is equal to 200 here. That is possible because it is mutable reference. What do you think? Will this code compile? No, it won't compile. So here it compiles. That is because ref1 is not used here. So that's why. So we'll use the ref1. I'll just create one more code statement here and I'll try to use the ref1. Let's analyze this code. Ref1 is immutable reference. This is mutable reference. Do you think this code compiles? Again, there will be an error here. As you can see, the error now is at this location. It says cannot borrow num1 as mutable because it is also borrowed as immutable. The borrow checking feature of the Rust compiler strictly enforces single write or multiple read policy. I hope you understand these concepts. Don't worry if it is confusing or something. So as we make a progress and write more exercises, it will be natural to deal with these things. So don't stress too much on these concepts. Please remember this. So it is single write or multiple read. In Rust, you cannot have mutable borrow and an immutable borrow of the same variable at the same time. This is to ensure that the variable state is not changed unexpectedly. Once a variable is borrowed mutably, any subsequent attempts to borrow it immutably will cause a compile time error and vice versa. Now let's get back to our slice data type. So as we discussed in the previous lecture, a slice is nothing but a reference. Now let's see how to create a variable of type slice. So now since we have already understood how arrays work, we'll understand slice data type in terms of an array. I mean, the same concept you can leverage to other data structures like string or vectors. A slice in Rust is a reference to a contiguous region of an array. It is represented by $t inside the square brackets. This would be the type of slice. So where t is type of elements in the array. If it is an array of I32 items, then the slice of this array would be of type square brackets I32. A slice allows you to borrow a portion of an array without taking ownership of the entire array. and provides a way to work with subarrays in a safe and efficient manner without having to make copies. So this you would appreciate while doing exercises. Now let's see how to create a slice. So now first let's create an array, and then I'll create array of I32 values. Let's say this is an array, right? What's the type of this array? So let me annotate the type I32 semicolon 4. This is not required, so just for clarity purpose I have written this. Now how do I create a slice of this array? Remember that slice is a reference to a portion of the array, some portion. The portion could consist just one element, or it could contain even an entire array. And we express the portion using the range expression. We'll see that now. So let's say I'll just take the slice, let me call it as S1 is equal to, let's take a slice from this array, use the square brackets here. So this is the 0th index, first index, second index, fourth index. Let me use the range expression. So let's say I'll use 1, 2, 3. This dot dot operator is called as the range expression. This is the start index and this is the end index exclusive. So this is exclusive. The portion consists items 2 and 3, not 4, because this is exclusive. And if you want this to be inclusive, then you have to use equal to sign here. Now this is inclusive. The end index is inclusive. That means items 2, 3 and 4. 2, 3 and 4 are part of the slice now. It's like that. But you cannot represent a slice like this in the code. So you have to use a borrow operation here. That is, you have to use a reference here. Now, as you can see, this is a reference. So this is an immutable reference to a portion of the array. And that portion is mentioned by this range expression. And let's see how to print the slice. You can use println. You can just print like that. So let's print S1 slice. S1 is a slice whose type is, what is the type of S1? Remember that, ampersand, square brackets and T. What is T? The items type, that is I32. Remember that. And a slice doesn't implement the display trait. Hence you have to use the debug trait. Use this format specifier here. Now let's run. As you can see, it prints 2, 3 and 4. That means this S1 holds a reference to this portion of the array. Please note that S1 is a slice. That means it's a reference. So there is a borrow operation here. Basically, it actually refers to that portion of the original array. Can we have multiple slices in the program which refers to the same referent? Yes, you can. Let's say S2 is equal to ampersand my array. Let's say I use the range expression dot dot. That means I'm taking a slice over an entire array. Or I can have a slice, so let's say S3 over, let's say 0 to 1 inclusive, like that. Can you guess the output of this program? This would print the entire array, and this would print 0 and 1 inclusive. That means this portion. Let's run. So why this is possible to create multiple slices in this program? Because all these are immutable borrows. There could be n number of immutable borrows, right? That's why n number of immutable slices are possible. Please note that when you create a slice, you specify a range of indices that determine which elements of the original array are included in the slice. The slice itself is a reference to this sequence of elements, and you can use it to read and modify the elements in the slice. Because a slice is just a reference to the original array, modifying the elements in the slice will also modify the corresponding elements in the original array. So if the original array is mutable. Similarly, any changes made to the original array will also be reflected in the slice. Note that slices can also be created for vectors and other collections in Rust, not just arrays. Here is a pictorial representation of a slice. So here is an array, and this is how you can imagine the array in the memory. So array is a contiguous data structure in memory. All these elements will be stored something like this. And here this portion can be thought of as a slice. This is a slice. And this slice starting index is 2, and I want to include 4 contiguous elements in the slice starting from 2. That's why I should select the end index as 6, not 5. One index more than actual inclusive index. So here 6 is exclusive actually. So this will not be a part of this slice. This is also one slice. Here the range is from 3 to 5. This whole array also can be thought of as a slice. Here the range is 0 to 8, like that. And those indices are written inside the square brackets. This dot dot operator is often referred to as the range expression operator in Rust. It creates a range of values, and it is used in various contexts to specify a sequence of values, such as for slicing arrays, creating for loops, and match patterns. This operator is called as range expression operator. And if you just check the documentation, so you would see all these different range expressions. For example, if you use start dot dot end index, then you observe here end is exclusive. But observe this syntax, start dot dot equal to end. So here end is inclusive. If you don't mention start or end indices, then a whole array will be considered as a slice. So here the start index is assumed as 0. So here you can assign any start index. Here the end index is not given. So from this index onwards, the whole array will be considered as a slice, like that. Now let's see how slice variable is stored in the memory. Let's say you have this array, my array, which is stored something like this in the stack memory in contiguous memory locations. So let's say the memory location starts from 200. So the first element is stored at 200, and each element type is I32. So 4 bytes are required. The next memory location would be 0 cross 204. There the second element is stored something like that. And then I create a slice variable. And let's say this is a slice. This is 0, this is 1. A slice variable is created in the memory like this. This is a slice variable. I mean, a slice is not a variable, it's a kind of data structure which will be created in the memory. And that data structure has two parts. This part is used to hold the reference to the array. Here array is the referent, remember. So two portions are created. One portion is used to store the address, and the second portion is used to hold the size information. Let's say this is the memory at which the slice is created. So let's say it is created 0 cross 400, which is not a useful information for us. Just I wanted to say that slice is a data type. It's kind of a complex data type. It has two portions. One is a portion where it stores the reference value. In another portion, it stores the size information. Here in this case, it stores the address 204 because that's the starting address of the slice. And the size of the slice is 4. Slice means how many elements are there in the slice, or to how many elements this slice refers to. We know that type of this array is I32 semicolon 8. This is the type of this array, and type of this is ampersand I32. That's the type of this slice. Please note that this is immutable borrow. Hence, you can say that this is the immutable reference. This slice cannot use this reference to modify the referent. The referent is in this case my array. So 0 cross 200 is memory location where the first element of the my array is found. 0 cross 400 is the memory location of the slice 1 where reference information is stored. 0 cross 404 is the memory location of the slice 1 where size information is stored. That's how slice manages that portion. So it has got initial address as well as the size information. So now we understood how this slice is represented in the memory, right? Basically in the memory, it is a fat pointer which consists of two portions. The first portion holds the reference to the portion of the array, and the second portion actually contains the size information. So now can we use this slice to modify this array? Let's see. First of all, here this is an immutable referent. That's why I cannot modify this array using this slice, but I can access the elements of the array using indexing into the slice. For example, let's say I can do something like this. I can, let's say, print the 0th index of this slice by using this syntax. What this would print? The slice is actually from 1 to 3. So this is the element at the first index. So this would print 22. So what if I make 5, let's say, which is not a valid argument for this slice? Let's see what happens. Here this could result in a panic. As you can see, this actually causes a runtime panic because here the index is out of bound. Because the length information which is there in the slice is 3, 1, 2, 3. But you actually gave the out of bound argument here, that is 5. So hence that causes actually a runtime panic and the program terminates unexpectedly. Suppose if I mention the argument 2, then that would print 444. Let's run this code. That's correct. Now we know how to read. So now can we also use this syntax in order to modify this array? So let's check that. For that, let's make this mutable array. Can I do this? So let's say s1 of 2 is equal to 100. Can I do this? So you cannot do this here. Why? Because you see this borrow. This is immutable borrow. So this is an immutable slice. Hence, you cannot use this slice to modify the referent, even though the referent is mutable. This would raise an error. As you can see, cannot assign to slice which is behind the immutable reference. How do we fix this? If you want to modify the referent using a slice, then you change this to a mutable borrow. Make this as mute here. Now here S1 is a slice whose type is ampersand mute I32, which is the type of this slice. Now you can modify the second element of the slice. What does that mean? Basically the slice was from here to here, and in that second element is this 0th element, first element, and this is the second element. This will be modified in the original array. So this would become 100. Now we'll print the array. So we'll see what is the content of the array now. Let's run. As you can see, this field is modified. In conclusion, please remember that whenever you are using slice, so basically you are behind the reference. Remember that. So you don't own the referent. So you are behind the reference. And you have to remember this diagram. If you ever get confused, so come back to this diagram, and this is how the memory representation looks like. Now let's understand how to iterate over the slice. For that, let's write a program that creates a slice of size 4 from a given array and computes the sum of all the elements in the slice and prints the result. Let's take this array. So now let's take this array, and then we have to create a slice of size 4. Let's create one slice is equal to ampersand array name. So I would say 0 dot dot equal to 3. This is a slice of 4 elements. Then we have to compute the sum of all the elements in the slice by iterating over the slice. For this, we can use a simple for loop for every I in my slice. And then, so let's create one variable here. Let's say let sum is equal to 0. So I can write sum is equal to sum plus I. But what is I here? First of all, my slice type is what? So type of my slice is ampersand I32. This is the type of my slice. Here I will be a loop variable whose type is I is a loop variable of type ampersand I32. Here I is a reference to this element. That means in the first iteration, I will be a reference to this element. In the next iteration, it could be a reference to this element. Since my slice is reference, I is also kind of reference. That's why I should write here sum is equal to sum plus star I, because I want the value. And after that, let's print this result. Now let's compile this code. I'm sorry, so here I should make this as mute. Let's compile. So the answer is 26. So now let's summarize what we did. So now let's summarize this discussion here. First of all, what we did was we created a slice variable which is a reference to a slice of integers. Here in this case, this is a slice portion. For each iteration of the for loop, the loop variable I is assigned a different reference to an element in the slice. Therefore, the type of I is a reference to an integer that can be written as ampersand I32. So the type of I is ampersand I32. When iterating over the slice, the loop variable takes on the value of each reference in the slice rather than the value of each element in the slice. I takes different references. I doesn't take different values. Remember that. So I take different references, hence its type is ampersand I32. Now in this code, even if I just write this, I'll remove this asterisk. So even if I do this, this will work. As you can see, it prints the correct answer. It doesn't result in any error. Why is that? Basically, it's like you can think of it's like doing I32 plus ampersand I32. I32 plus ampersand I32 because I is of type ampersand I32. So don't you think there will be an issue doing this operation? No, actually. What happens here is whenever the compiler sees this plus operator, it invokes the add trait implementation of this data type I32. Now let's analyze the add trait. Let's go to the standard library and let's search for I32 primitive type. And as you know already, there will be a section called trait implementation. Here is a add trait implementation, different flavors of add trait implementation for I32. And here is one implementation, implement add ampersand I32 for I32. As you can see, the implementation accepts argument of type ampersand I32. And this implementation will dereference this reference to retrieve the underlying referent value, which is I32, and it performs the addition. Hence, this is a legal code because the trait implementation supports that. Even you can do I plus sum. This is also a valid, so that is ampersand I32 plus I32. So even you can use a reference here. When I use a reference here, this is also a valid code. So what happens here is, this is like a kind of pattern matching. Let me explain why this code works actually. You may be thinking like, when I use ampersand I here, anyway I is already ampersand I32, so this would become something like ampersand I32, something like that. That's not true actually. What happens here is, so we are iterating over a slice. Then for each iteration we'll get a value of type I32 in this case. And that I32 value will be matched with this pattern. So this is a pattern, remember. So the pattern is ampersand I. Hence there is a pattern matching here. So I32 will be placed into I. So this is a pattern. Hence the I32 value will be placed on the I variable. Hence the type of I here is I32. Type of I is I32. So we can prove that. Let's bring our earlier code of type checking. That was this code, and we will print the type here. Let's say type of I. So I have to send ampersand I here. Don't worry about this code. This is just to prove the type of I actually. Let's run. As you can see, the type of I is I32 in this case. Think in terms of pattern matching. There is a pattern actually. So this value is extracted into I. Hence I becomes of type I32.